Welcome to Robotics and Automation News webinars, where you can be part of a global event without leaving your home or office. Attend our live webinars and communicate directly with influential professionals in your industry.
Hello, my name is Abdul Montakim. I'm editor of robotics and automationnews.com. In this interview, I speak to Duann Scott, Vice President at nTopology, which is a software company whose main offering is what's described as a next-generation design and engineering software application. Unlike other industrial design software applications, which tend to include generative design as an additional function, nTopology puts generative design front and center of its workflow. The nTopology application can also work with other CAD software, so users of popular 3D design software do not experience any disruption to their work. Duann explains better than I can in this interview.
My name is Duann Scott, and I'm VP of Business Development at nTopology. And so what I do is I work with partners to connect nTopology to other software, hardware, consultancies, and education, and then sort of help our customers have a good experience between those different platforms.
Right. And tell us a little bit about nTopology itself, the company.
Yeah, so nTopology is a design engineering software formed in New York City in, I think, 2015. And we have a different approach to making geometry. It's not traditional CAD. It's a different process whereby it's a computational design tool. And so we help engineers and designers solve problems that traditional CAD cannot solve due to geometry issues in existing CAD. So we can do very, very complex things very easily, and we can automate processes. So often people aren't designing a single part, but they're designing a process, and the output is parts in the end.
It's a very interesting area and company as well. And I know we want to talk about something that you've recently done, a case study, which we'll get onto in a minute, about robot grippers. But I find the whole area of 3D printing and new what you call next generation design and engineering very interesting. And I wanted your overview of what is changing and the extent of the changes and the timing of those changes. And when I say those changes, I mean essentially mean 3D printing, really, because to me it feels like it's still a new area with technologies being developed, metal being something that I don't know if I'm correct, but it's still not quite capable of doing certain types of metal, like steel, the hard, difficult things that require a great deal of high temperatures to melt and shape and things like that. But what's your overview of the changes that are happening in manufacturing as a whole as a result of the emergence of 3D printing?
Sure. So additive manufacturing started off as rapid prototyping, and it was just plastic parts to make prototypes to see things fit. And then the industry moved on to things like jigs and fixtures. And now as the processes have evolved, now people are designing end-use parts. And particularly in metal 3D printing, the material palette has opened up massively in the past 5 to 10 years. So we're at the point where you can manufacture super alloys and copper, stainless steel, titanium, Inconel, like very, very high value materials, because the industry has been driven by the aerospace and medical industries. And so the machines have evolved where you can do very, very complex componentry, very complex designs with very fine details and fine features. But the software that people were using to design for it was built for subtractive manufacturing, for tooling, for molding, for stamping. And the software could not create the complexity that the machines could make. And so this is sort of how nTopology was really born, was to unlock that potential of the manufacturing processes by using a different way of approaching geometry. And really, it's critical to redesign for these processes because the cost of the machines and materials is still quite high. And so to really get the value, you have to design for the process. Because if you take an existing machining design and put it into a 3D printer, it's not going to be cost effective. But if you take that design and optimize it for multiple requirements, whether it be the manufacturing process, thermal process, for lightweighting, for even other functions around acoustics, you can do all those simultaneously and then also consolidate multiple parts into a single component and really drive value from the machines. And so that's where we are now, is ensuring people understand that this design process is critical for extracting the value from 3D printing.
Mm. This is on the screen, as hopefully audience can see. I'm visiting the nTopology website, and there's a lot of very interesting images. I could talk about lots of them, but this one in particular has caught my eye because, as far as I understand it, you can correct me if I'm wrong, I'm sure you will. This is a I think it's a robot arm. So the lines,
Yes.
yeah. So the lines represent what the traditional or the original design, the conventional design would look like. It would be all these spaces between the lines would be filled with material and be solid, and that would form part of the robotic arm, the industrial robotic arm, and
Correct.
the colored parts are the bits that a process called generative design would have sort of automatically, I don't know, as I say, correct me if I'm wrong, but as I understand it, that's something that the computers, the software has helped generate to try and save on materials. And that is the key, as you mentioned, the amount of material used in subtractive design, all of that would all be largely wasted, maybe recycled, but only a certain percentage of things get recycled. So yeah, it's a very 3D printing, additive manufacturing is a very efficient process when it comes to actually building parts. And this particular one, I don't know how, has this been actually implemented by any robotics companies? Because the majority of the robotic arms that I see still have the conventional historic sort of design.
We've seen some built like this more towards the R&D or like bespoke robots. So what's happened here in this design in particular is that you're correct that the wireframe is the original body designed in CAD from the assembly for the robot. So we've taken that component and we've applied simulation stresses and constraints on the component. So we have the mounting points and where the stress is. We run simulation on that, and what it's really showing is the load path of the stress. So as the robot's moving and lifting things and orienting itself, this is where the stress moves through the component. And so where we don't need to have mass, we remove the mass, and so you end up with a lightweight part. We can then go do a secondary process, and we can then run the simulation again, and we can then shell the part, so make it hollow. So again, we reduce greater mass out of the part, and also reduce the manufacturing time. We run a simulation again, and then when there's stress, we change the thickness of that shell so that the actually skin of the part is thicker where it needs to be and thinner where it isn't to be. So it starts to sort of go in the process of how a bone might be generated in the body. So the bone continually modifies itself based on the stresses that are on it. And then we can go in and do a lattice infill just to make it more manufacturable, in that you wouldn't need support structures inside. So that's sort of the approach that we take. So that's really topology optimization. When you think about generative design, what you're doing is you're generating multiple outputs and comparing them to each other. So we would run a script, like you might run it overnight, and then in the morning when you come back to work, you might have 1,000 variants of this design, and then you can compare them to each other based on the mass, the performance, or some other criteria you might have. And so that's sort of the approach we're starting to see. Where I've seen it done for real is at Oak Ridge National Labs, whereby they designed this robot arms. It was actually a fully articulated robot that had all of the wiring and any other components built inside of the part as well, so you wouldn't have any exposed cables or wiring. Was all really self-contained. I think that's for an underwater application. So you can do very, very complex things with this process and with high quality materials.
I'm very interested in this part because I keep thinking that it's going to catch on. More and more robot builders are going to use this type of design. But as I say, at the moment, the majority of the pictures that I'm seeing through our website still have the original.
And the other thing we're doing now as well with partners is not necessarily printing the final part, but printing either a sand mold to cast the part, or printing sacrificial components for investment casting. So you could print it in a lower cost polymer, and then coat it with a ceramic, and then pour metal into it. So you have the same known process that's been around for thousands of years in the end, but just we're sending the design in a different way there.
Here it is again. About materials, just one quick question, I suppose, is as I say, as far as I know, I mean, again, you're the expert. As far as I know, metal is either difficult or time-consuming for 3D printers to produce. Is there alternative materials that are just as strong, newer alloys and maybe different plastics and things like that can do the same job as metals?
Yeah, the cost in the metal printing is in the amortization of the machine cost, which can be expensive. But the actual quality of the materials is very, very good. There's, so what we, as I mentioned before, what we're seeing people starting to do is to print polymer parts and cast them, or to print sand molds and cast that is a cheap way of doing it. And there's also some processes where there's high quality polymers and also carbon fiber layups on parts as well to make them stiff and strong.
And I don't know if you'd want to do this, but I'm kind of wondering what the percentage of the potential 3D printing or additive manufacturing has fulfilled so far, in terms of how much of the industry, if you like, has adopted it. What percentage of manufacturing that could be done through additive manufacturing is currently done by additive manufacturing?
I'd say it's tiny at the moment. So as I mentioned before, what's leading the industry is aerospace and medical. So in medical and dental, it's pretty much, if you aren't adopting additive manufacturing, then you're falling behind. So spinal implants, knee reconstructions, bone plates, surgical guides are all very much leading the way, because they're small, they're expensive, and they're custom to each customer. So the customization is critical to make sure that you don't put the same implant into a 8-year-old child as you do it to a 40-year-old man who's 240 pounds. So you always modify the design for that particular person. And in dental, everyone's teeth is different, so a lot of scanning to manufacturers going on, and that's going in both metal and polymer. So that's where it's really leading it, and the adoption's really, really strong, and we start to see it expand as people learn more about the process, and the cost of the machine and materials comes down over the years, which has been happening.
Aerospace is it's very interesting because there's kind of a tentative move towards developing electric aircraft, lighter, which kind of suggests, or maybe there's a separate parallel development towards lighter aircraft. Is that, you know, that, and they're using more 3D printing? Is
Yep.
that something that, I mean,
Yeah.
you've already suggested that is the driving, one of the driving factors of the growth of
Absolutely.
additive
Yeah.
manufacturing.
Absolutely. Yeah. We do have customers doing electric vehicles for space and flying. I don't think I can tell the name, but yeah, every ounce that you save reduces the the structure that's required to carry it, and also the battery power to run it. So everything you do that reduces weight increases range, and so it's critical, really.
Mm. And it's not just the traditional or very large aircraft manufacturing companies, whether it's Boeing, Airbus, or all the other long established companies. There are drone companies emerging that would
Yep.
probably be looking at mass
Yeah.
production of things.
Yeah. One of our customers, Cobra Aero, started off designing the engine head for the single cylinder engine that they run for the UAVs they make, and they started off just trying to consolidate parts, so taking three parts into making it into one, and then from there we also worked with them to lightweight the head of the engine using ladder structures, and also cooling the component using ladder structures. And we did this all based on simulation, so we can take the pressure map from the engine, the heat from the engine, and we'll use that to modify the ladder structures to optimize it and and make it way more efficient, way lighter, and and less components, like three components into one. So there's no assembly, there's no fasteners, there's no gaskets, so it's less maintenance as well. And we can also do things like attenuate the acoustics, so reduce the sound, which is, you know, critical for a drone that's trying to not be seen.
Mm. Yeah, it's all very interesting. There's a lattice structure that you mentioned. Is that something that's particular to your company? Or is that something that's kind of industry wide?
It's ladder structures allow you to modify the behavior of a material without changing the material. So it's used a lot in additive manufacturing. So you can make a a component crumple in a certain way, or absorb energy, or reduce its mass, or change the way it flexes. So we, in polymers, you see it in helmets and padding and seating for cars, and also like this helmet here. Um, in metals, we use it to tune material properties for thermal applications, so like making a heat exchanger. People use TPMS structures, which is a triply periodic minimal surface, to change heat. Here we have COVID swabs. So these swabs were developed in like a week and approved in 2 weeks, and were being manufactured using a DLP system, like 3D printing polymers, and they outperformed the existing swabs that were designed. Here we have the helmet that was designed for NFL. There's a number of helmet companies using this now, but Impressio won like a $490,000 grant from the NFL to develop helmets for the NFL to stop concussions, using ladder structures to help absorb energy and stop the twisting of the head during impact. So you can really change the way a material behaves using a ladder structure, and that's what we call them meta materials or architected materials. There's a lot of what's happening in additive manufacturing.
Okay, and one last question before we go on to the specific case study. Your company offers a particular separate, distinct piece of software, does it, or does it?
Yes.
Yeah. So
Yeah,
tell us about that.
we're purely a software company. We develop the software from the ground up. Existing CAD systems are based on, they're really based on taking drafting or drawing and putting it into a computer. And that was developed in the 80s. And the kernel underlying all of that, the way the geometry is created, is a BREP. And because it's developed so long ago, it was developed for single-threaded computers, and there's inherent issues in complexity, which was never ever conceived of doing geometries this complex with a CAD system. And so what we do, we have a different way of creating geometry it's basically a mathematical equation. And all we're doing really is using a formula to define a product. So we can do something very, very complex like this heat exchanger, and the file size for this would probably be 160 kilobytes. Whereas if you tried to do this in CAD, it would be gigabytes, and it would just, you couldn't do anything real time like this in a traditional CAD system. So it's purely a mathematical equation which describes geometry. And we also have what we call field-driven design, which is whereby we can use any data to drive the way a geometry behaves. So whether it be simulation data or empirical testing data, or just other geometry to help define the way the geometry behaves. So in this case, this is a prosthesis where they're adding a surface structure to make it stiffer. And if they wanted to, they could take, and here we're having, this is simulation data. So this is a pressure map from somebody standing on a pressure map for their foot. And then we modify the lattice density based on the force going into the shoe sole. So we can make it denser to absorb more energy where there's more pressure, and then make it sparser where there's no pressure, so we can make it lighter. And so we can, we see people doing this to optimize a shoe for someone with diabetes. If they've got some issues with their feet, we can help relieve pain and make a custom shoe sole specifically for them. And this is all possible because the underlying geometry, complexity is not a problem for us. So, and then often the parts are so complex, it's other softwares that you might need for downstream processes, whether it be simulation or for manufacturing, can't handle it. So we have our internal simulation, and then for manufacturing, often send manufacturing data direct to machines, because any software which is sort of in between us and the machine can slow things down.
Yeah, I still find it quite amazing that 3D software, 3D design software can be accessed and used through the cloud. I mean, this is a cloud-based. Can this be accessed through the cloud?
Ours is completely local. We don't run on the cloud yet. And this is because most of our customers are aerospace and defense and medical, and they're not really, in most cases, ready to have their designs up on the cloud. There's too many security issues and ITAR issues. So yeah, but we can conceivably do it. We have people running it in servers, but as it stands, the software is local. And because we've optimized for multi-core CPU and GPU, like our application engineers just run it on a Dell laptop. They're not running a supercomputer to make these really complex designs, because we are so efficient in the way that we describe and modify geometry.
Right. Well, my point, the reason I mentioned those, because I just find it amazing that, as you say, standard computers can run 3D design applications. Because I grew up, thinking, and even now actually, my computer struggles with 3D design applications. It is an old computer; it's about 7 or 8 years old.
Yeah.
So it often crashes.
It's because the underlying kernel for the geometry isn't multi-threaded, and your computer probably has 4, 6, 16 cores, and it's using one. And so what we've done is, because ours is a mathematical equation, we can run, you can see the block we have, you can see 5 blocks here. We can run all of those simultaneously. It's not a hierarchical system. It's non-linear. So, and we also use the GPU acceleration. So if you have as many cores as you have in your GPU, we can use that as well. We just leave, we'll eat up every resource on your computer to generate geometry, and we can do it really, really fast. So we can send you a license and you can test it out and see.
Thank you very much. I appreciate it. I find these things really, really interesting, and I only wish I could. I knew enough about 3D design to make things. I've tried to learn, and I just find it really interesting. And certainly, I do want to do something which I'll mention specifically, talk about later. But it's basically that robot arm, the part that I was talking about.
Yeah.
I wanted to use it as a trophy for our awards.
Oh, cool.
Planning, but I'll tell you about that in a minute, because I just want to dwell on this, because I don't want to mention the name of the company. The trainer company is very famous, biggest in the world, I think. I don't need to name them, but they developed or designed many years ago. I think about 30 years ago now, but they designed something with an air bubble in the sole, which even without knowing anything about 3D design or trainer design or any kind of design, it just seemed a very silly idea because you're talking about two-level sole
Hmm.
in a trainer with an air bubble in between, and the connection between the athlete's foot, the actual person's foot, and the ground is broken by the air bubble, which means
Hmm.
that any very forced, fast interaction is disrupted by the air bubble, which it just did not seem like a very good idea. So it's very interesting to see this that you're doing where you're saying that the heat map is shown there, and
Oh yeah.
therefore the sole in between the foot and the ground will be designed according to where the pressures are and where the reinforcement needs to be, where the strength in the trainer needs to be. So it's
Oh,
I mean
we can also reverse it out. So this is for absorbing impact. We can reverse out and make a ladder structure which acts like a spring and rebounds and basically pushes you off. So
mm,
yeah, so we can really tailor how a material behaves using these geometries.
yeah, in tennis and any kind of fast-moving sport, it's very important that the connection between the athlete's feet, and the ground are true, are very accurate, and yeah,
Hmm.
the bounce might actually help. Yeah, it's very interesting what's happening to design as a result of this kind of software and 3D printing and simulation and all that. So it's very interesting to observe. Okay, just to quickly, I'll mention about what I was saying about this thing here. We are planning robotics and automation news as a website has been going for about 5 years, and we haven't done an awards thing that everybody else does. All publications and websites tend to have an annual awards.
Hmm.
We haven't done one so far, and this is the first year that we were going to do it, and we were hoping to well, design a trophy ourselves. We may have to just settle for a, standard sort of style awards, which we can buy off the shelf from
We can
one.
help you out. We can help you out with that. So the
Yeah,
interesting thing about nTop is when you, as I said, we don't really, you can design a part, but you design a recipe. So we can give you a workflow where basically you can take the 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 outer geometry and the stresses and constraints, and you can modify it yourself. You can change a few parameters, and then you're basically making your own robot arm based on the recipe we give you. So we can give you a head start, and then you can modify it. So this is what the value is really, yeah, cool.
yeah. This is basically what I wanted. I know the
Yeah.
details are different. This looks obviously very different. These gaps and things are very different. I just wanted a plinth, a base
Hmm.
there attached to the arm, which obviously is I mean, it would never have a plinth. I mean, this is for a robotic arm, so the plinth is irrelevant. But as an award, I think it worked quite well to have a plinth there and
Yep.
have it stand upright. And on the plinth, we could write the names of the winner and things like that. So,
Yeah,
yeah,
easy.
I'll
We can help
discuss
you
that
out.
with you. Yeah, I'd love a bit of help. As I say, I've tried myself to design things, and this would be my biggest achievement ever if I could do it. So yeah, let's go into the case study. We saw, we talked about a very interesting thing that you've been doing. As it says here, agile industrial robot grippers with topology optimization and metal 3D printing. Tell us about that a little bit while I play the video.
Yeah. So it's a customer of ours that had issues getting grippers made. Traditionally, they invested hundreds of $1,000s in this robot, and any downtime is that machine's amortized, and their business isn't as efficient as it should be. By redesigning the gripper, they've been able to get more accuracy and less downtime and less errors. And so they can now run their robot 24 hours a day, lights out, with no issues. And so when you think of it, there's, hundreds of thousands of dollars worth of investment in this factory, and this one small part was holding them back from, getting all the value out of it. And so by optimizing the design, going from this machined version to a 3D printed version, which was kind of similar to it, but with a bit of improvement on the grip. And then the next iteration, they optimized the geometry as well as the grip area so that it could be more efficient in how it approaches the tooling section. So it would not, because it's a smoother transition there, it wouldn't bump into the other component it's holding and stop the machine. So no more downtime for them. And then now once they have this, and it's printed in a desktop metal machine, which is they have in-house access to, it takes a couple hours to print. You then need to sinter it to sort of melt the metal material together, and then you've got a functioning part. So then once they have any change required, so if they're doing a different process or they have a different geometry they're trying to fold or a different material or thickness, you can just change the recipe here in nTopology and the design will update to meet those requirements. So you don't have to start from scratch next time because you already have your plate, you have where it's attaching to the robot, and all you do is modify the requirements and the geometry will update itself. And then we smooth out topology, mesh it, send it to the machine, print it, and you're golden.
Is it a big market, this then? The end effectors or
yes, yeah. I think that anyone who needs to custom manufacture a end effector usually goes to get a CNC machine. So it's a block of steel somewhere. They have to design it in traditional CAD. They send it out and it comes back a few weeks later and you hope it works. With having a 3D printer at close access, you can iterate. You could do 5 iterations in one day, print them all, test them all, and pick the winner. So even though we're using simulation to define what the geometry looks like, you can do a few iterations and the cost of manufacturing is fairly low. So you could just run it through, test them, and then the winner you have in your, you keep that recipe in nTopology, and then next time you need to make a new version, use that as your seed point. And so you're sort of learning as you go, and you're sort of embedding your engineering intelligence into the software as you go. So it's not a black box. So a lot of the people who are putting out generative design, it's kind of like a black box. You have your design, you send it up to the cloud, you get something back, and you hope it works, but you can't really see what's going on in the design process. With nTopology, you have access to all the buttons and levers to make it happen. So you can see what's happening, you can learn from it, and you can modify it, and then you have that IP that you can use for your next design. And that's what we're seeing happening here.
And is this a market that you're particularly interested in, or is it just one of the markets that you're interested in? What are the markets that you tend to? I know you've mentioned aerospace and medical and things like that, but what are, going forward, what are the areas that you think might grow for you?
Yeah, we're seeing, like, we had early adopters in medical and aerospace, and then we're starting to see automotive, heavy industry, just general manufacturing, consumer electronics, consumer products, sports goods. So it starts off being where higher performance parts that are going into a assembly is what people are going for first. But then if you think about the things that make things, they can make a huge difference to whether a product going to market is financially viable. So like these guys moving from a day shift to 24 hours manufacturing is huge for their business. And it's not a sexy part that goes out that people see. It's not a bright color for a Bugatti. It's a small part which holds something, which makes something. The other area where additive manufacturing is used a lot is jigs and fixtures. So holding the thing that you've just made so you can inspect it or machine it or assemble it isn't sexy, but it's required everywhere. And so we worked with Stratasys to make a jigs and fixtures workflow and a masking workflow so that someone can just drag in the geometry and make a jig or fixture without spending hours in CAD making a thing to hold a thing. So there's so much opportunity to not just make really complex, high performance parts, but also to automate the design, engineering, and manufacture of things that people don't really want to work on. You don't make a jig because you want to make jigs. You work on a jig because you need to hold something, and that's sort of what we're looking at as well.
Mm-hmm. And what's it like marketing? And I don't know how, whether it's nTopology is very new. Maybe you can tell me while you're answering. But what's it like marketing, if you like, a new piece of software into a market where there's a good number of 3D design software applications available for people to use? I mean, how do you do it? How do you get clients in such an environment?
The additive industry is fairly well aware of us, and there's been a need for this. So we don't replace CAD, we don't replace simulation, we don't replace build prep software for setting to machines. We sort of augment it and improve it. So no one uses nTopology standalone as a single piece of software with nothing else. So in the additive industry, it's not too hard for us to communicate the value because it's been required and there's a hunger for it. And so it's just about, finding the person with budget. But there's, everybody who's working in additive needs a tool like this. What we need, what is the challenge is educating people on how to use this new approach to creating geometry. So it's not drawing a line, it's not emulating traditional design software in that you don't draw lines, extrude things, round things, and then make a drawing from them. So when you're 3D modeling in CAD, you're really doing that so you can make a drawing to send to somebody to manufacture it. With ours, you're defining your requirements, you're outputting a geometry, and you're sending that geometry to a machine to manufacture. You don't tell people how to make what we do. You tell the machine to make it by sending it manufacturing instructions. So that's a step in approaching design. And then, so that's one challenge in marketing this software. The other is, making sure people are aware that we can solve either really, really complex problems or just automate problems which are kind of boring. The more complex ones are easier for us to target because someone who's designing a heat exchanger, like you can see in the top right-hand corner, they're used to having complex issues they need to solve, and they're looking at simulation packages to do this. And and we work with those simulation companies to make sure that we can get our geometry into their tools as efficiently as possible. So we'll work with ANSYS and Abacus to make sure we can optimize getting thermal data in and out of nTop into their systems. And so by using those networks that exist, we can sort of spread around there. But it's a less sexy applications which are harder to market to. So finding someone who's designing jigs probably isn't looking on the internet for jig software. So we have to target them in a different way.
I think I understand what you're saying. I mean, as I say, I've had a go at various 3D design applications. I understand what extrude means and drawing lines and things like that. I found it very complex, really difficult. I've done what you might call 2D design for many, many years. I've used applications like Quark Express, InDesign, to design magazines and newspapers, and I was, that was my job before. But 3D design I found very, very difficult. I just could not understand the concepts of how to connect different parts and have them extrude in certain ways and curve and things like that. This would be very difficult for me to make. And what you're talking about is a different approach. I mean, I can't say I understand it fully, but the idea, almost like putting generative design at the center of it, you're instructing the computer to produce something based on what your parameters and your requirements are, rather than approaching it from the other traditional drawing board direction, if you like. So I kind of understand it. Yeah.
Yeah, with a lot of, most people they start in CAD, and when they hit the wall of what's possible in their CAD software, then they bring it across into nTopology to do the things which the CAD can't do, and it's not always something you think is hard. So things like a paper pulp mold. When you're making the mold, you need lots of holes in the mold to suction out the moisture, and like doing that in CAD, you've suddenly, if you've got 1,000 holes, suddenly you've got 2,000 edges of the circles, and I don't know how many faces will be required, but it's suddenly really, really geometry complex. But it's a simple thing, and for us, we can put 100,000 holes in a mold in 26 milliseconds, and you blink and it's done, and the software is totally fine, because it's just a mathematical equation which defines where they are. So, and if you were doing in traditional CAD, you have to draw the pattern of all those holes, and if it's conformal to a surface, like the mold isn't flat, it's curved, like if you're molding like a paper cup or something, or some packaging for a computer screen, it's really, really complex. And so doing that in traditional CAD is just basically impossible. So we don't say, I'm going to draw, you say, I need this amount of holes in this direction, and press go, and it happens. So it's a very, very different approach. But as I said, we don't replace CAD, we just augment it.
Yeah, I remember I designed a bit of furniture, a wardrobe, and I ended up with, I don't know, hundreds of parts, even though it's a fairly simple wardrobe, hundreds of parts, hundreds of files within files, and it was very, very difficult to...
Yeah, and if you make one change to a component, then it all blows out, and you have to go back and fix all these things. Those rebuild errors don't happen with nTopology, because it's a mathematical equation. All you're doing is adding an integer or a value or some other component to the equation. So it just works.
You keep saying that it doesn't replace CAD, but is it something? Can people use nTopology without having to resort to anything else? Is it something that can do an end-to-end design, production, and everything?
You can, but most people don't. Like I've designed things where I've just used nTop and nothing else. But traditionally, you're making a high-performing, well, a lot of times making a high-performing component that goes into another assembly. So it needs to connect to other things. So you might do the whole assembly in CAD, and then the tricky part you might bring into nTop, or multiple parts and consolidate them and then make them perform better. So it is possible, but it's not the most usual use case.
Okay. All right. Well, it's been really, really interesting talking to you. What are your plans, do you think, of it as a company? How do you see the next year, 2 years, 5 years unfolding for you?
Well, that's a big question. We're going to continue to develop the tools within nTopology and broaden out potential applications. So we work a lot with our partners to find use cases that are problematic for their customers and help solve those problems. We'll continue to develop a desktop software. We'll probably move some aspects to the cloud for those who want to use it, and maybe make other solutions which are just simplified for pure applications. So maybe something like we did with Stratasys for the jigs and fixtures. Maybe we'll do a medical workflow and a heat exchange workflow, so people can get to value faster without having to learn everything about the software. They can just dig in and start using it on day one.
Great. Is there anything that I didn't ask about that you'd like to mention?
I think the thing, like we started out doing a lot of geometry for additive manufacturing, but we are also used for other manufacturing processes. Like our biggest consumer electronics customer does not use this for additive, but uses it for other machining processes for cooling of componentry. So there's lots of potential when you have when you need to automate a design, make something complex, or sort of simplify a workflow for repeatability and modification. Like we're here for you.
Okay. All right. Well, thank you very much for your time and your insights. Good luck with everything, and
thank you.
And I'll talk to you about the other thing, the possibility of maybe designing an awards trophy.
We'll help you out for sure. And thank you for the opportunity to talk about nTopology and what some of the cool stuff our customers are doing with it.
Thank you. Take care.
Thanks.
Send us an email at sales@roboticsandautomationnews.com to register for one of our many upcoming webinars. And if you'd like us to host your webinar, we have a range of options, including long-term lead generation packages and marketing campaigns. We look forward to hearing from you soon.